Hello everyone, my name is Grigor Mukurchan and I'm going to talk about the partial differential equations, and I'm going to start with the heat equation. So the first thing I will start about the heat equation, before we start and talk about the heat equation, I will just want to introduce one concept so everyone will be familiar with. That concept will come up a lot. Some of you might know, some of you might don't know, but the concept is the conduction. The conduction, which is the result from the collision of neighboring molecules in which the kinetic energy of vibration of one molecule is transferred to another. So the conduction is just the interactions between the molecules, which one has the higher kinetic energy, or in this case, like higher temperatures because of the law of the because of the thermodynamics. We know that average kinetic energy is proportional to the average temperature of the temperature of the particles. So these concepts will be very useful in our discussions for today. So we're going to start with considering we have a rod. So suppose we have a rod which has a constant cross-sectional area A. In this case, we're gonna assume that all the thermal quantities are constant across the cross section. So assume all thermal quantities are constant across the section. So for right now, we're gonna only talk about the one-dimensional rod. So first, we're gonna assume that the lateral surface is insulated, meaning that no conduction is occurring through the surfaces, or no thermal energy can pass through the lateral surfaces. So what we're gonna looking for is to derive our heat equation. The heat equation, and our unknown variable, we're gonna have some unknown variables that we don't know. Like the unknown variables can be, so the unknowns variables is the thermal energy density, which would denote as E of x t, thermal energy density. So if the rod is not uniformly heated, so we can say that the rod thermal energy density varies from one cross section to the another. The basic concept of density, with density actually means how does the given quantity distributed. like the mass density, meaning how the mass distributed in given system, and in this case the thermal energy density tells us how much the thermal energy is distributed across the rod. If it's uniform, then our density is constant. If it's not uniform, then it's not constant at all. So suppose our cross section started from x equal to 0 and x equal to L, and we're going to consider very thin slice of the rod located at the position x and x plus delta x. Well, I know by the image it's not thin at all, but we're gonna just assume it's a thin. Now, if our thermal energy density were constant throughout the volume, then the total, we can say we can rephrase our total energy in the slice is the product of total energy and the volume. So if let me write that down. So if our thermal energy density were constant, the rod volume, therefore our total heat energy of the slice can be rewrite. So we are looking for the total heat energy of the slice. So since our thermal energy density is the amount of thermal energy per unit of the volume, so we need to figure out how much heat energy are in this slice. We have to just multiply its thermal energy to the volume, and the volume of this thin slice can be referred as the length multiplied to its cross-section area. So I can rewrite as the thermal energy density times the area times the length of the slice. So here I can define this as the volume of the thin slice. Okay. Now the heat energy within this slice, via changes in time, due only the heat energy flowing across the edges, and also the heat energy that generated inside within the slice. So what does it mean? So if I have heat energy enters to the slice and the heat energy is exited out the slice, the difference between the rate can vary within the time. And moreover, we can say that there are some sources that contains with this slice that also produce the given heat energy. So verbally, I can rewrite whatever I said in terms of this. So let's say the rate of changing heat energy on time. So the total heat energy with respect to time within this slice is the heat energy flowing across the boundaries. So it's the heat energy flowing across the boundaries. Since we are looking the change in rate with respect to time. So we're gonna also assume per unit of time. Plus the heat energy generated inside per unit time. So this can be based on the conservation of we can call this as a conservation of heat energy, right? The conservation of heat energy. The total heat energy is just the sum of the energies across the boundaries and the heat energy that generated per unit of time. So I can rewrite this as the conservation of heat energy. Conservation of heat energy. Okay. Now, this is, since we are the mathematicians and not the not the English people, so we would like to rewrite this in terms of equations. So, as noted here, we define our total heat energy within the slice as the thermal energy density multiplied with the volume. Since we are talking about the with respect to the time, the change of rate with respect to the time, so I can rewrite this as the partial. I can rewrite this as the partial of our total heat energy with respect to time. Now, now let's talk about our second concept, the heat energy flowing per unit of time across the boundaries. In mathematically and also in physics, anything that flows across a certain cross-section, we call it a flux. We have an electric field flux, we have a magnetic field flux. Now we are talking about the thermal energy flux or heat energy flux. So suppose we have a thermal energy, so we know that there is a thermal energy flowing across into the boundaries and outside the boundaries. So we define this as a heat flux, which is amount of thermal energy per unit of time flowing to the right or per unit of surface area. So we can redraw our diagram as, so our heat flux, let me just write it down here, what I just said. The heat flux, which we'll define as the phi of xt, heat flux, which is the amount of thermal energy per unit time flowing to right, to the certain direction, but in this case to the right, per unit of surface area. Right? If you remember from physics class that our electric field or the flux is the magnetic flux or electric flux, is just to find the integral of electric field multiplied to the cross-section area that passes through. Similarly, the heat flux. So, suppose our heat flux across the x is the phi of xt. So we are looking at the certain time t, and the flux flowing across this boundary is just going to be f phi of x plus delta x t. Okay. Now, if our heat flux is negative, it means that our heat energy is flowing to the left. Simply, we choose our positive direction is to the right. Now, to define our heat energy flowing per unit time across the boundary slice, so now we are looking for the heat flux within these boundaries per unit of time. Now, here at this boundary, the flux is entering, so is going at this boundary is going in. So our heat flux across in this region is going to be positive. But since at this boundaries it's leaving out the slice, therefore our heat flux will be negative. So therefore I can summarize this as, like, I can rewrite this: the heat energy flowing per unit time across boundaries of slice. So I just need to find the total rate of the heat flux that entering in and exiting out. So the heat flux itself is already contains the per unit of time. It's just the rate itself. Now, since as we agreed again that here at this slice the heat flux is entering into our slice, and at this boundary heat flux is entering, so our total heat energy flowing per unit of time across those boundaries is gonna be phi of x comma t times the area minus phi of x plus delta x times the area. Since our cross-section area we choose to be constant. Now, if these both terms are positive, the heat energy flowing per unit of time at x contributes to an increased heat energy in a slice. Whereas the heat flow at x plus at these boundaries will decreases the heat energy. Okay, so let me catch it what I said. The heat energy the flowing per unit of time at this slice, if it's positive, meaning it contributes to increase the heat energy within the slice, where if this term is positive, this term is positive, then the heat energy flowing across this boundary is causing to decrease the heat energy in the slice. So therefore, I can rewrite the heat energy flowing across the boundaries per unit of time in our equation as T times the surface area divided by x plus delta x comma T times I. Now, the heat energy generated inside per unit of time. So over the heat energy that generated within our slice, we're gonna just call it as period of time, we're going to just call it as the Q of xt, which is the heat energy generated. But now, which is like heat energy density that generated, how uniformly dense it generated or distributed. And since that's our density, we want to know the heat energy generated, we're going to just multiply with area times the delta x. So therefore, this is our equation form of the conservation of heat energy. Conservation of the heat energy. So therefore, now I can do simple math, simplify my math. So let me just rewrite our conservation of heat energy. Now, the conservation of the heat energy derivation. So I have partial t of E of xt times the area times the delta x, which is equal to the phi of xt area times the area minus phi of x plus delta x of the time at that time a, and plus, apologize for that, q of xt as area times delta x. Now divide everything by the area and the delta x and take the limit of that infinitely small, like delta x, to 0. So if I everything I divide by a delta x, so therefore if I take the limit delta x approaches to 0, partial e partial t, that's equal to the limit as the delta x approaches to 0 of phi of xt minus phi of x plus delta x, apologies, over delta x and plus our q of xt. So let me just rewrite this. So here there's no delta x, so this is left with as a partial t. Now, so let me just kind of rechange this so you can see how I going from there, or how I got the result. So if I factor out the negative, it's gonna be x plus delta x t minus 5x t over delta x. And if I take the limit as x, it's just going to stay as q of xt. Now, this is just the definition of the derivative, isn't it? It's just the definition of the derivative, differentiation. So just I can rewrite this as the derivatives of our heat flux with respect to x. So therefore our changing rate of heat energy density with respect to time is equal to negative of the phi partial x plus our q of xt. So this is our formula for the conservation of heat energy. Okay, our formula for the conservation of heat energy. So we're going to further simplify this or do more substitutions to get the more accurate answers for this, like the more generalized equation. The reason why we're going to do that, because we have many unknowns in our equation and we only want to solve for only one equation, one function. We only want to one function because we have only function of our heat flux, which is also a function of x and t, and we also have a thermal energy density, which is also a function of our position and time. And this is heat generated. Heat generated is just the information that they need to provide. It could be neglected, it can be like this is the heat energy found within this, or there might be some relation between our heat energy and our unknown function. And I will tell you which unknown functions that we're going to use it to simplify to. But now, let's look at the same conservation of heat energy in a finite segment. Since here, we were looking for infinitesimally small segment, so now we are looking for the finite segment. So let's write again the conservation of heat energy in finite segment. Okay? So let's consider another rod. Consider another rod, and it going from 0 to L. Now let's say our finite segment located at x equal to A and x equal to B. Okay, so we are looking. So again, we can define our heat flux across the boundary A as a phi of A comma T, and the heat flux across the boundary B as the phi of B comma T. And let's say this is our cross-section area is still a constant. Now, again, we are looking for the one-dimensional rod. So, to find the total heat energy, which is the sum of contribution of infinitesimal segments, slices. So all these things we have just did for the very infinitesimal small segment. Now we have the millions of them, of those segments, is infinite amount of this segment is within our segment, within our slice. So what we are looking for, so to find the sum of all those total heat energy, in order to find the total heat energy within this segment. To do that, we can't just divide into the fragments, amount of fragments, and then we get the accurate results, approximate results. But to get the more accurate, we have to convert our Riemann sum into an integral. So therefore, I can rewrite this as the partial derivative of my heat energy density B E of dx, which is, now my heat energies across these segments is just equal to final minus initial. It's just the total heat energies across the boundaries. It's just the amount of heat energies enters and the amount of energies leaves. So it's going to be phi of AT minus phi of BT. And then plus the heat generated density within that segment. Now I can use, so my integral only depends on x. since I'm integrating with respect to x, and since my thermal energy density is multivariable with respect to position and time, so therefore this integral is just depends on time because I'm integrating with respect to x and I have an upper and lower limits. So therefore I'm going to substitute those numbers and I will get rid of the x, and the only component I left with this equation is the time. Therefore I can use the Leibniz symbol, the Leibniz rule, which is the differentiations under the integral sign. So I can rewrite this as the integral going from a to b as the partial of e partial t dx. Now here I can use the fundamental theorem of calculus. So I can rewrite this as the integral from b to a, right? So I can partial phi partial x dx. I just did the fundamental theorem of calculus. Now why I do go from b to a, not from a to b? Because if you remember fundamental theorem of calculus, when we integrals with respect to x, differentiation of x, which is differentiation is antiderivative. Sorry, integration is the antiderivative. So the antiderivative of derivative is the function itself, and it's going to be upper limits of that our function minus the lower limits of our function. And again, plus a to b of q of dx. Now, I can rewrite this because all my integrals are going from a to b. I can rewrite this by just swapping it from a to b and introducing a negative sign. So therefore, I'll get from a to b of partial a partial t dx. That's equal to negative going from a to b partial phi partial x dx plus a to b q of dx. Now from here I can take everything on one side. So going from, since all of them are integrating from a to b, so I will get from a to b partial e partial t plus partial phi partial x minus q dx is equal to 0. So this is equal to 0 since there are only two cases that this integral can be equal to 0. The one case is when the both upper and lower limits are the same. But since when our slice is going from a to b, where I didn't specify it, but where the b is greater than a, and we can by logic say b is greater than a because our positive direction is to the right, as I mentioned earlier. Therefore, therefore this integral is equal to 0 if and only if our integrand is 0. So therefore, I can write that my partial e partial t plus partial phi partial x minus q is equal to 0. And therefore, I want to little bit do some rewrite this same equation, and I will get it's equal to negative partial phi partial x plus q, and which is the same equation as the conservation of heat that we got it earlier. Why I wrote it smaller, I didn't just realize it. So this shows that no matter like how small or how large or how finite or how infinitely small your segment is, you still this equation is still applicable. It's still applicable. Now the new concepts that I will introduce: temperature and specific heat. Heat. The temperatures in this time, since we have a letter T for time, to avoid from the confusions, we're gonna symbolize our temperature as U of xt, and our specific heat as the C of x, let's say. Well, the specific heat is something that doesn't change over time because it's a property of material. Now, so the question is, how does it doesn't depend on time, but does depend on x, which I will answer your question this soon. Now, in our partial differential equations, we're gonna use the temperature to describe the material. So we are not going to describe the material based on the thermal densities, but we're going to use the temperatures to describe our materials. And our unknown function at the end of our conservation heat equation is going to be our temperature. And the specific heat is the energy required to be supplied to the given mass of the substance to raise the temperature just by 1 unit. So if the units of the specific heat is going to be the unit of energy, let's say joules per kilogram times degree Celsius, which is amount of energy required for a 1 kilogram object to raise the temperature by 1 degree Celsius. 1 degree Celsius. Similarly with other units, but the most common one in physics specifically, very useful, the joules per kilograms degree Celsius. Now, as I mentioned, the specific heat or the heat capacity doesn't depend on time, but it only depends on x. Why it depends on x? Well, it depends on the structure of our, in this case, rod or the material. If our rod only consists of one material, then it only has one specific heat. But if our rod consists of an alloy, which is like a metal solution, so with changing the positions, it will change its specific heat. Now, recall the thermal energy in a slice. So our thermal energy in the slice is defined as x of t times the area times the delta x. We can also describe our thermal energy as the energy it takes to raise the temperature from the reference temperature to its actual temperature. So I can rewrite this as aka that's equal to C of x times our mass times our temperature difference. Let's say our initial temperature was 0. Our reference temperature is 0. This is the same equation. You might see this equation in physics. The Q is equal to mc delta T. So that's this equation comes from mass times specific heat times change in temperature. Now, if I do a little bit of mathematics, I can rewrite the equation for our thermal energy density as specific heat times the temperature multiplied by the mass over A times delta X. And if you notice, this is just the mass per unit of volume, which is the mass density. So I can rewrite as this C of X times the rho of X, the density, mass density, times the U of xt. Okay? So, just let me rewrite this as a 1. As a 1. You will see why I wrote 1. That's because we want to represent everything as an unknown function, which is the temperature in this case. Now, right now, let's understand some properties of heat flow. Okay, so 1. If the temperature is constant in a region, so no heat energy is flowing. No heat energy is flowing, and that makes sense. Why there should be heat energy flows if there's no temperature differences at all? If my body temperature is same as yours and we handshake as for the greetings, you will realize like nothing will happen. You will not feel a cold or nor hot, and I will never feel the cold nor hot. But if there are temperature differences, therefore the heat energy flows from hotter region to colder region. And this comes from zeroth law of thermodynamics. So if my hands are really cold and your hands is gonna be really warm, first we're gonna feel some temperature differences while greeting each other and shaking our hands. So one thing you will realize that my hands will become hotter while your hands will become colder, because your hand loses energy and my hands loses energy. And the third one, the greater the difference in temperature, let's say we are talking about the same material. Therefore, the greater is the flow of heat energy. And the last but not least, the flow of heat energy will vary for different material even with same temperature difference. The reason is because it depends on the material's conductivity. To summarize all of these properties of the material is into single equation that will be make sense to have, is called the Fourier's law of heat conduction. Fourier's law of heat conduction, which says that our heat flux is equal to the negative of the thermal conductivity times the partial U partial X. As a K naught is our heat conductivity, thermal conductivity, which is measures the ability of materials to conduct the heat. Since our K depends on the type of the materials, therefore different materials conduct heat differently. Because the different materials conduct the heat differently. So the larger our K naught, the greater the flow of heat energy with the same temperature differences. So the materials with the low K naught value is just the poor conductor of the heat energy. So let me just write this down. The K naught is defined as the thermal conductivity So the higher K naught, so the greater the flow of heat energy, the greater flow of heat energy. The lower the K naught is just a poor conductor or insulator. It's just a poor conductor. Insulator. Now, let me rewrite this as our equation 2. Now, substitute our equation 1 and 2 into the conservation of heat equation. Now, so our thermal energy density defined as the specific heat times the mass density times our thermal energy density, our temperature, and our heat, our heat flux, the heat flux is just with this equation, and we can substitute into our heat equation. Now, one thing to notice, K naught can be depend on X if the rod is not uniform. It's not uniformly made. Now let's assume rod is is made of one material. Therefore, now I can substitute that. So partial t. Now instead of E, we're going to substitute this expression. So C times rho times the U of xt, that's equal to negative partial x. So I'm going to substitute our Fourier's law, which is going to be negative k naught partial u partial x plus our q of xt. Now I can re-simplify this. So that's going to be c times rho as partial u partial t. That's equal to k times partial u. So it's going to be second order derivative of u with respect to x plus our q. So now this differential equation is kind of much more easier than the other one because I only have one unknown function that I need to solve. Now not in case of q equal to 0, my equations become 0 partial u partial t, that's equal to k naught second order u partial x squared. Now I can rewrite this as partial u partial t is equal to a k times partial u partial x squared. So this k, the k is equal to k naught over the specific heat times the mass density. This is defined as thermal diffusivity. So if you remember from biology or from chemistry, the diffusion is just the how going from a high concentration to low concentration. So the heat energy that's initially concentrated in one place and then the distributed or diffuses through it to become a lower concentration. Now this given heat equation will describe how heat energy spreads out the diffusion. So now this given also the heat equation also can define as the diffusion equation, which is like can called as aka the diffusion equation. Okay, so this is for our first video. The next topic that we're going to talk about is called the boundary condition. That's our next topic. Thank you so much for watching my video and see you soon.